Hi, class. Today we're going to go over polynomials with complex zeros. First, let's look at the complex conjugate pairs theorem. If a plus bi is a zero of a polynomial function with real coefficients, then the complex conjugate a minus bi is also a zero. And what you want to remember here is that I is equal to the square root of -1. So it is a pure imaginary number. Let's look at our first example that illustrates this theorem. Example 1. Let p of x be a polynomial with the zeros x is equal to 2 and 2 minus 2i, where p of x is equal to the quantity of x minus 2 times the quantity of x minus 2 minus 2i. So just notice here that the factor x minus 2 corresponds to the 0, 2, and the factor x minus 2 minus 2i corresponds to the 0, 2 minus 2i. Also notice that this 2 minus 2i, this is a complex zero with an imaginary component. The negative 2i is an imaginary component, whereas 2 is just a real number. Now, if we go ahead and expand our polynomial and just go through, distributing, you can kind of go over these steps if you want to pause the video and look at the steps. But we end up with x squared plus the quantity of -4 plus 2ix plus the quantity of 4 minus 4i. So these are actually complex coefficients, right, with imaginary components. So our polynomial is not a function with real coefficients. Okay, we have some imaginary components here. And if we look back at our theorem, this complex conjugate pairs theorem tells us that if you have a plus bi, then you must have its conjugate, a minus bi, in order for the coefficients to be real. Well, that wasn't the case here. Okay, here we had 2 minus 2i, but we did not have its conjugate. Its conjugate would have been 2 plus 2i. And so that's why, if you notice here, we end up with some complex coefficients. So that is the conclusion here. P of x has coefficients with imaginary components when there's a complex zero with imaginary components, but its conjugate is not a zero. Let's look at another case with example 2. This time, let p of x be a polynomial with the zeros x equals 2. We've got the 0, 2 minus 2i, but we also have its conjugate, 2 plus 2i. So this is a different type of case here, where p of x is equal to the quantity of x minus 2 times the quantity of x minus 2 minus 2i times the quantity of x minus 2 plus 2i. So again, this factor x minus 2 corresponds to the 0, 2. The factor x minus 2 minus 2i corresponds to the 0, 2 minus 2i. And the factor x minus 2 plus 2i corresponds to the 0, 2 plus 2i. And again, I'm just going to repeat this. Notice that we do have the conjugate pair here. Okay, we have 2 minus 2i and 2 plus 2i. And so when we go ahead and expand our polynomial, if you want to go ahead and just pause your video, you can kind of read through the math that we have here. But as we expand our polynomial, the imaginary components are going to disappear. If you notice in this final step that we end up with x cubed minus 6x squared plus 16x minus 16. So these are all real coefficients. We don't see I anywhere. And that just has to do with the fact whenever you have conjugates that are multiplied, well, middle terms cancel. And then whenever we have the end term that has the I, whenever you have I squared, if you look here on this step, is equal to -1. And I made that the comment here that, well, I is equal to square root of -1. So it should make sense that I squared is equal to -1. And this problem is a little more complex, so it might be a little bit hard to see the middle terms canceling on the conjugates, but I'm just going to show you just a really simple one here so you know what I'm talking about. So let's just say that we have a plus bi, okay, and we multiply it by its conjugate, a minus bi. So when we go ahead and distribute, we have a times a, which is a squared. We have a times negative bi, which is negative abi. We have bi times a, which is bia, but I'm going to go ahead and just write it as abi. It just looks a little bit better. And anyways, we can move these around because of the commutative property of multiplication. And then I have bi times negative bi. So that's negative b squared I squared. Now, when I was mentioning the middle term canceling, Now, when I was mentioning the middle terms canceling, I'm talking about these terms here in the middle. We have a plus and a minus. If you have a positive and a negative of a number and you put them together, you get 0. So those end up canceling. So I end up here then with a squared, okay, minus b squared. And then remember that I squared is equal to -1. And I'll go ahead and just write that over here too. It's good to just have as a reference. And so when we simplify this, we get a squared. You got minus minus, that's going to give you plus b squared. So no longer do we have the imaginary component there. Whenever you multiply by the conjugate, the imaginary component disappears. So here's our conclusion. P of x has real coefficients when there's a complex zero with imaginary components and its conjugate is also a 0. So that's what we see in this example. We have this complex zero that has an imaginary component here of -2i, but notice its conjugate to plus 2i is also present as a 0. So whenever we expand our polynomial, notice there are only real coefficients. The imaginary number I does not appear in any of the coefficients here, just real numbers. So that's what this theorem is saying. And so this is going to be useful when we go to factor polynomials and find our zeros, because you know that if you have a polynomial that has real coefficients, if you start solving and you find one of your zeros is imaginary, then its conjugate must also be a 0. So we want to keep this in mind.